Okay, so this is the video recap for Module 3. There are going to be two parts to this video recap, so this is just going to be part 1. So Module 3 basically, basically a topic on which where we see how we check the regression assumptions, right? Whether those assumptions are met for our particular model, and if certain assumptions are not met, then what are some ways in which we can remedy the problem so that we can still continue with our modeling. So what are the assumptions for a linear regression model? In mathematical form, it's basically saying that your errors, right, are so IID means independent identically distributed. So that means these error terms are all independent and they all follow a distribution, a normal distribution with mean 0 and variance given by sigma square, right? So this is the mathematical form of the assumptions. Now, if you prefer to think in more regular language, the byproduct of the previous statement has these following meanings over here. So the first assumption, right, could be viewed as that the error terms for each fixed value of x have mean 0. So that means if you look at, x equals 2, is the average of the error is 0, right? So for every possible value of x, is the average value of the error is 0. The implication of this term is that it implies that the relationship as specified in your regression equation is appropriate. So if you think about how one thinks of the regression framework, we typically could write it in this form, right? We say that it's your response is equal to some function of your predictor plus the error terms. So if this function is correct, or it's a good approximation for the general relationship, then the errors, right, for each fixed value of x should have a mean of 0, right? So for now, we're usually focusing on a situation, right, where we typically say that this f of x is basically this linear relationship, right? So if the errors have mean 0, then it's basically saying that this is a good approximation. You could decide, depending on your particular situation, right, to have a squared term added, or in later topics, in later modules, we'll look at more complicated versions of the model. Right? So if you have mean 0, it means that this form of the relationship is appropriate. The second assumption, the errors for each fixed value of x have constant variance. That means the variation in the errors is theoretically the same regardless of the value of the predictor or the fitted value, right? Because the fitted value is basically given is basically a linear transform version of your x variable. So it's basically saying for when x equals 2, the variance of the errors should be the same as the variance of the errors when x is a different value. The other part of the assumption is that the errors are independent. The consequence of assumption 3 is that the observations are independent. So that's what the third assumptions mean. The fourth one, that the errors, right, for each value of x follow normal distribution. So what we'll be focusing on in the rest of this presentation is how to detect issues with assumptions 1 and 2 and how we fix them. The part about independent errors, i.e. that the observations are independent, is typically a byproduct of the data structure and whether you had a random sample. Because if you have a random sample, then by definition, right, the observations will be independent. So then the errors will also be independent. So we'll be focusing on seeing how we can see the first two, assess whether the first two assumptions are met, and then later on we'll talk about how we fix those issues. Generally speaking, if the assumptions are not met, then your results from your hypothesis, test, and confidence intervals are no longer reliable. One thing I'll note though is that it has shown that the model is fairly robust with normality assumptions, so it means that your results are still reliable even with some deviation from this assumption. So the fourth assumption regarding normality is the least important of the bunch, right? So people have published papers and done studies to show that it's not as important as the other three. So how do we assess assumptions? We create what we call a residual plot. It's basically residuals on the y-axis and the predictor or the fitted value on the x-axis. So this is only in simple linear regression. When we go next into multiple linear regression, you have to use the fitted y on the x-axis. So some features we want to look for: residuals should be randomly scattered across the horizontal axis because this implies that the average is 0 for each value of x. Residuals should not display any pattern. That's also another thing we want to look for, and if that happens, then on average, right, the residuals are 0. The other feature that we want to look for is whether the spread, right, spread is just another term for variance of the residuals for each value of x or each fitted value is constant. So this is how we assess the constant variance assumption. So this is an example of a plot that is ideal. So this is like the idealized plot. And some books will say if you can fit them in a horizontal band around the x-axis, that's what we want, right? Because so what we see is that for each value of x, right, the average tends to be 0. So, right, if you look at this subset of your residuals, right, for small values on the x-axis, the average of all of these, right, are about 0. So for any sub-region on your x-axis, right, are the residuals on average 0. And generally speaking, that's what we see. So that's an even scatter on both sides. The other feature that we look for is whether the variance is constant. So it's basically for each value of x is the spread, right? So that's the spread of the residuals for this particular value of x, right? And we can see that's the spread. So it's pretty constant, right? That's the spread over here. That's the spread over there. So this spread is pretty much the same as one moves from left to right. So this is the idealized plot that we have. What we have here is an example where it's not met. So this is not met because the average is not 0 for certain subregions. So if you look at, say, this subregion of your residuals, right? So for small values on the x-axis, these are all negative, right? So the average here is not 0. And then if you look at this subregion over here, the average here will be positive. And then if you look at this subregion over here, well, the average here is negative, right? So if you look at each of these subregions, right, if you had residuals that were looking like this, then the average is 0, but that's not the case. So, right, here we see the mean is not 0. The other thing we notice is this curve pattern, right, which we don't want to see, right? So we notice there's a curve pattern. So this is basically implying that the mean of the residuals is not 0 for each. It's not 0, right? So the function that we have, whatever, so as I said, so far usually we've been starting from this linear function, is not a good approximation for the data, and we have to do something to that. Now in this example, the variance is constant, right? Because if you take a look at the vertical spread, it's still pretty much the same as one moves from left to right. So the constant variance assumption is okay with this example over here. This next example is one where the variance is not constant because initially, right, that the residuals are all very close to the horizontal axis, but then as you go from left to right, you notice that the spread of the residuals get a little bit bigger, right? So some people say that this is like a funnel shape rather than a horizontal band, right? So in this case, the variance is increasing, right? So it's not constant. The other thing is if you want to see if the mean is 0, well, the mean does seem to be 0, right, for any subregion. So if you take a look at this subregion, your residuals do appear to be mean 0. So any subregion that you can form, generally speaking, right, the average is 0. So the average of the residuals do appear to be mean 0, but the variance is not constant, right? So we've taken a look at the ideal plot and two different plots where, right, one of these assumptions are not met. Obviously, you could have a situation where, right, you could have both not being met. So this wraps up part 1 of this recap, right? In part 2, we'll talk about the remedial measures when we notice these features in our residual plot.